Okay, finally, this is the last section of our Unit 4. Guess what's coming this week? Okay, end of the week. So use exponent and logarithmic functions. The continuous exponential growth function P of t equals P sub 0 e to the kt, where the population depends on time, and P sub 0 is the initial population. All right, what's that mean? This is how much you start with. Your initial population, or your initial amount. Okay, and then you know E is a number, and K, it's sort of like just like R, so this could be related to that PERT formula, if you will. You know what I'm talking about, the old continuous compounding, right? So this is, there's a lot of things in nature that can be modeled by this situation, by this formula. In 2000, the world population was estimated to be 6.124 billion people. This is going to be your initial value, P sub 0. And then they give you a scenario, and it says in 2005, it was 6.515 billion. We are no longer in the same situation. So how much time has passed? All right, so 5 years. So we're going to use a T of 5. So I'm just showing you how to pick apart the word problem. Now, where is this 6.515 billion going to be if that's P sub 0? Meaning, I'm going to be popping in everything I can into the formula, and I'm going to have to determine the value of K. Okay, so far I've got a T, I've got a P sub 0, the initial population. What's this thing going to be? E is a number. You don't ever substitute anything for E, it's not a variable. So this will be your P of T. Okay, that's going to go in for your P of T. All right, so here we go. So we're going to do an equation. We're going to put in 6.515 for the P of T. That's equal to 6.124 times E to the K. And what is our time? 5 years. 5 years since 2000. All right, so then we are going to solve this. First, we're going to need to divide by 6.124 and get a nice, lovely long decimal. 6.515 divided by 6.124. And I'm going to go out more decimal places than we are in these numbers. I'm going to go out, say, 4 or 5 decimal places. 1.06385. And that's going to equal my E to the, I'm going to just flop those around, 5K. Or K times 5, it really doesn't matter. And now, since we're in the logarithm chapter, what are we going to do now? So because we solve for an exponent. I can't change bases or anything, so what can I do? From the last lesson, take the log of both sides, or in this case, maybe we should do the, there you go, natural log. All right, so the natural log of 1.06385 equals, let's use our power rule, bring that 5K out front times the natural log of E. And we learned that the natural log of E is 1. So here's what we're going to do to get K. We're going to take the natural log of 1.06385 and we're going to divide that by 5. And that's going to give us our K. Okay, so I'm going to go back to my calculator. Check this out. I still have this division we did in here, so I'm going to use it. I'm going to hit second, ln. Oh, no, not second. I don't need to hit second here. Oh, poop. I just lost what I had there. I'm going to try to get it back. Oh, all right. All right, second, I got to try to go back. I just wanted to get that answer back, and I blew it. All right, so that was a waste of my time. But anyway, natural log of, and I can type it in. I was going to show you how you could type it in without having to type all of the numbers. You could have put it in using that second negative key and put your answer in. I think I rounded to 5 right here, didn't I? Just for everybody to have the same thing. Don't forget to close that parenthesis before you hit divide by 5 or hit enter first and then divide by 5. Okay, so you should have 0.01238, and that's your K value, which is about, says what is the relative growth rate or rate of growth would be about 1.2% growth. Because then when will the world's population reach 7.5 billion people? Well, we found the K value. So now we could write a formula that would include the K value. But we're going to be putting in 7.5 billion for the amount of people that we have. So that's going to be our P of T. And we're going to be figuring out the time it takes. So let's go ahead and put 7.5 billion equals, for P of T, equals, our initial population was 6.124. And we had times e to the k, and we know our k value now is 0.01238. But we don't know the time. So you have to put a t in for time. Or an x would work, but we're not using that graphing calculator right now, so let's stick with t. To solve this, we would need to divide by 6.124 again. So divide 7.5 by 6.124. Okay, I got 1.22, blah, blah, blah. Let's jot that down, 1.2246. And then I think after that was a 9. Yes? Okay, e to the 0.01238t. A lot of decimals. It's just kind of tedious, the little details we have to write down on these. But we have to have the decimals be to these long places, at least 4 or 5 places out. Take the natural log of both sides. Bring the t out front. Oh, and the 0.0. I just wrote that a little wrong, so I'm going to fix it right away. 0.01238t times the ln of e. ln of e, of course, is 1. So just to find the time, all we have to do is take the natural log of 1.22469 and divide it by 0.01238. That's what you type. I would definitely be practicing typing these if I were you. I think 1.22469. Close it, divide that by our lovely 0.01238. Okay, about 16.4 years. Now, about 16.4 years, or the year 2016.4. Now, I had a question I posed to my, pardon me? No, well, it depends on how the question was worded. So it said, estimate the population. Wait a minute, what did it say? When will the population reach? When would be about the year 2016.4. It said when, so you would give the date. Now, question, what is 0.4 of a year actually? I just love that question because that's not correct. It's easy to just think a quarter. I know what you're thinking. If you said 3 months, you just divided by 12 months by 4. That's not what that means. 0.4 is 4.8 months. 40% of a year, of 12 months, is 4.8 months. Right? All right. But it's just where your brain goes. And I understand. So just remember, if you were asked, it's probably a better answer to have it in years and months, but whatever. Okay, just a little aside. Use this exponential growth function. All right, same thing. A population of bacteria grows exponentially. An initial population, oh, right there, there's my P sub 0, grows to 2,500. Where's that 2,500 going to be? That P of T. And it's happening in 4 hours. Just remember your time is in 4 hours. In hours, not years. Right? The function for this population of bacteria is a function of time. Then estimate the population at the end of 16 hours. So we have the 2 steps. Step 1 is to find your K value. And that's by using the situation of those 2 different values. So we got 2,500 is equal to 1,000 times e to the K, and we know how long it took for that particular growth rate, 4 hours. We're going to divide by 1,000. That's going to give us 2.5 equals e to the 4K. We're going to take the natural log of both sides, bring that exponent of 4K out front. Remember that the natural log of e is 1. So we just have to take the natural log of 2.5 and divide it by 4 to get our K. Okay, so once we have our K value, we will be able to estimate the population P of T after 16 hours. We'll be doing the P as 16. So let's get that value quick. Natural log 2.5. You guys probably already got it. And that's getting divided by 4. So you got 0.2291. So our equation is going to be, still the initial value, initial part was 1,000, times e to the 0.2291 t, which you'll use an x if you were doing it on your calculator. This is just going to give, what am I supposed to put in for t? 16, all right, sorry. So you're just going to get the answer right away by plugging this in, because this is all a number. So we go and type 1,000 times, I guess I didn't have to hit times, but I did, e to the 0.2291 times 16. Hit enter. So how much bacteria is that? It's about, let's round it, about 39,080 bacteria. Gross. Okay, so that's an approximate value, because we've been rounding the whole entire time. Okay. Number 2, we got a special savings account grew exponentially due to interest from $5,000 to $5,682 in 1 year. 1 year. Oh boy. That's the key right there. All right. So initial value, P of 0, P of T is going to be the 5,682. What's our time? Notice that's in bold because people usually forget to let T equal 1. If the account continues to grow at this rate, how much will be in the account 5 years later? All right, so let's put in our 5,682 equals 5,000 times e to the k times 1. So we've already got k all alone. Divide by 5,000. 5,682 divided by 5,000 would be your first step. This one's going to find us K really quick. 1.1364. And that equals e to the K. And now we take the natural log. And that's going to equal K times the natural log of e. We know natural log of e is 1. So we just have to type in the natural log of 1.1364. Okay, and that was 0.12786. And that's my K value. All right, now I'm going to use that to find how much will be in the account 5 years later, which would be the P of 5. You still had 5,000 to start with as your initial value. Am I going too fast for anyone? Let me know. All right, times e to the, okay, 0.12786 times 5. Did I write it down wrong? There was a 5 at the end of that? Or is that, what number is this? This is number 2. I'm just going to look at my notes. I had 0.1279 when I did it the last time. It was, are you sure that it's a, oh, so then we could have put this as a 7, you mean? Yeah, sorry, honey. I totally don't know how I didn't see that on my calculator. So I rounded incorrectly if I did that. Then 1.278. Yeah, that should have been a 7 then. Actually, I've gone and just done 9 here before. If you just went 4 places, I'd be fine with it. So, yeah, it will happen. No, it will happen. So if I probably should say to you guys, to at least go to the 4 places. I'll look on your, like your work, check. But I'm not messing. All right. I've decided to stop my recording for just a moment. Okay. So being reminded that I had, rounded incorrectly, I definitely had. I don't know how I did that. And I went 1 more decimal place than I had when I did these notes before. 1.787 is what I should have had in for my K value if I'm going to go 5 decimal places. I like to go 5, but 4 is probably sufficient. It'll help us get the same answers. So what do I have to calculate there? I forgot. 5,000. Then I got to hit e to the, find my e, 0.12, and I think I said I went 787, and then I have the time now is 5 years. Okay, let me see how different that was than when I did my, now it is a little less money than if I had rounded to the nearest 10,000. So $9,476.24. Scott? No, unless you went and rounded to the nearest 2 decimal places. That's not, you can't, do not do that. At least go as many as your problem has. So I say, just be safe. Go at least 4. And don't bother with more than 5. Is that good enough for our K's here? All right. Don't try a hundreds place or something. It's going to really throw it off a lot. The bigger the numbers, the more it's going to throw it off. Okay, in an account where interest is compounded continuously, again at a rate of 5% a year, there's $41.25 in the account after 10 years. So I got P of 10. I got a rate or a K, if you will, of 0.05. And there's that much in the account after 10 years, so that's going to be a P of T. So that means we want to know what P sub 0 is, because it's saying what's the original amount in the account. All right, so we're going to put in the $4,125 in for P of T. We'll have a P sub 0 in our equation because we don't know what it is. That's times E to the 0.05 is our K times 10. Follow why the R is a, do you realize that this formula is almost just the PERT thing and anyway, right? Okay. So we need to, I'm going to multiply that out and divide by it. This is just a number, guys. So we don't have to take the log or anything on both sides. We can just divide by e to the 0.5. And where I got 0.5 from is I just simplified 0.05 times 10. Okay. So let's calculate that. 4,125 divided by e to the second ln e to the 0.5. You got $2,501.94. And that would be your initial amount, or the amount you started with, the amount in the account. Okay, number 4, we've got fossil remains, carbon-14 dating. You know, probably heard of that. And that's just got to, oh, look at that special little exponent they figured out. Whew. Negative 0.00012T. I sort of sound like that guy in the log thing, remember? All right. All right, this formula, is this really any different than what we've been doing? What's the A? It's like in the last problem, A, P sub 0, and this would be your P sub T, and that'd be your K, and this is your P or X or whatever. All right, so this formula is used for carbon-14 dating, where A is the initial amount of carbon-14, and T is the number of years that have passed, and Y is the amount of carbon-14 remaining. So I pose this question: how much of your carbon-14 do you have right now? How much of your carbon-14 do you have right now? There you go, 100%. You've got it all, because you haven't died. What? It's when you pass, guys, that you start losing your carbon-14. Okay, it's hitting age of fossils, so I just like to, I'm just being a fool. All right. So anyway, how old does a fossil, like me, remain that has 95% of its carbon-14? It's lost 95% of its carbon-14. So pretty old. So let's find out how old it is. What does it have left of its carbon-14? All right. So let's read the formula again. A is the initial amount of carbon-14. What's your initial amount of carbon-14 always? 100%. You've got it all. Okay, so we're going to put in 1 for A. We're going to put in the 5% for what we've got left, 0.05. Okay, so that would be your in this your Y, if you will, for this problem. Okay, and that equals 1, the amount you had originally, times e to the negative 0.00012. And what are we putting in here? We've got a time. We do not know the time. Okay, so we're going to take the natural log of both sides. Bring that lovely exponent out front. ln e is 1. We're just going to need to take the natural log of 0.05 and divide it by the negative 0.00012. I never write the zeros in one place, at least not much. I know you're supposed to, especially for the sig fig stuff, because it counts, right? Crap zeros and all that fun stuff. All right, natural log 0.05 divided by, and I forgot the icky number, negative 0.123000012. Okay. You guys probably already had it already, but that thing is 24,009. You know, in science terms, they probably would say it's about 25,000 years old, but 24,964 years old. Okay. About 24,964.4 years old. Okay, now let's say you found a skeleton in your backyard and it had 95% of its carbon-14 remaining because you took a bone down to the lab or however they do it. Okay, 95% left. That means now it's kind of the flop of what we just did, isn't it? So we're going to put in 95%. And you guys, aren't we just going to do a calculation and replace a number or two? Okay, you're basically just going to calculate, instead of the ln divided by negative 0.00012, you're going to hit the natural log of 0.95 and divide it. Don't forget that parenthesis if you're going to type that all at once. Okay, so this one is only 427.4 years old. Sorry, you guys. Okay, next question is about half-life. What does half-life mean? Half-life. Okay, I better explain. Half-life of a substance is how long it takes for it to decay to half of what it was originally. Some substances take a long, long time to decay. Can you think of something in our landfills that we really wish that wasn't there because it takes so long to decay? Yep, there you go. That's what I was looking for. Styrofoam. Anybody know how long it takes for styrofoam to decay? It's ridiculous. Okay, and it's man-made. So anyway, it's synthetic. So I digress just to get your attention. Let's go on. We got A is the amount of substance remaining. P is the time that's passed. H is the length of the half-life of the substance. So somebody's already figured out possibly the half-life. The half-life of an isotope is 415 years. Which one is that? The length of the half-life of the substance, that would be our H. So I know you might want to think time because it says years. But that's the half-life length of time that it takes. If there are 15 grams of the isotope at a recorded date, how much is left 200 years later? We're going to need to let that initial amount be 15. So that's going to be our A sub 0. All right, so here we go. We're going to do amount. I can do this problem without doing this formula, but I'll show you that after I do it with the formula. So you got 15 times 1/2 to the C. What's C? 200 years later. So we're going to do 200 divided by 415, the half-life number. And it's saying for us to find in 5 how many grams are left, and that's all we got to do is type this in. 15 times 1/2 to the 200 divided by 415. I'm hoping you got 10.74 grams. Does anybody need me to type that on my calculator that's here with me? Obviously, I can't answer someone if they're watching. Okay, I'm not going to type that one in. A radioactive substance has a half-life of 32 years. Now, if you want to use the half-life formula, we could. Or I can show you how to do it with the basic formula. A of T equals E to the KT. Okay, so how much do you have and how much do you have left is how you would want to think about this. If you're talking about half-life, how much is left when you have half of it? Half of it, right? So we're going to think of 1 1/2. So I could put a half in for what's left. I could put 1 in for the, ours was that anyway. Our initial amount would have been 1, the constant, and we're going to figure out the constant K. And K times 32 years it takes for that stuff to get to the half-life. You might like solving it better with just constantly using this formula. All right, these are not absolutely necessary. Okay, so here we go. Take the natural log of both sides will give us the natural log of 1/2 equals 32K times the natural log of E, which is 1. Natural log of E is 1. So we can do the natural log of 1/2 divided by 32, and that'll give us our K value. So to find the constant K. Okay, I was kind of getting tired of typing these in, but I shouldn't since I expect you to. Natural log 1/2. I can just type 0.5. And then I got to divide that by 32. negative 0.02166. And that's what it told us to find. Find the constant K in the decay formula. Doubling time. Okay, now we got a new formula for the doubling time. Use the formula P equals initial value again times 2. 2 for doubling. P is the time, and D is the doubling length of time. The length of time that it takes to double. T is the time that has passed as normal. Okay, Harlem City has a doubling time of 7 years. That is your D value, doubling time. In 2008, its population was 132,000 people. How many people will it have in 2010? Okay, so we have an initial value of 132,000. That's going to go in times 2 to the, we're trying to find how many people will we have. So that'll be P of T. How many years have passed? 2008 to 2010. Just 2 years. So that's 2 divided by 7. How long it takes for the population to double. So predict how many people there will be. And that's simply pushing buttons. Are you getting 160,900 and what are we going to round to if this is people? 10. Okay. Right. Okay, this next question, quite important. It will appear on your test. And not only that, it's one of the most missed questions on your unit test because of people not doing the homework. All right. Logistic growth. Let me ask you a question before I start this problem. How many people can we fit in this classroom? How many students could we have in here? Without looking at my contract. Could you fit more than 35 people in here? Would it be, what if we had 50 people in here? It would be very uncomfortable, wouldn't it? If they had to have a desk, each person, we wouldn't be able to, how are we going to get through the tables? You need a desk. All right, so there's another way to think about it. So it depends on the circumstances and what you're going to do. We're not going to pile and stand on top of each other either, are we? So are you going to actually fill the whole volume of the room? And would that be feasible? And would you be able to sustain that? No, you can't sustain that. No one's going to be happy and learning if they had to be in my classroom and there had to be 50 plus people in here. It's just too much for the room, the space, it's just not comfortable. So the point being, there is a limit, right? There has to be a limit. That's called the saturation point or the logistic growth. It's a logistic growth problem. So if you think about, why do they have deer season? Control the population. Why does that possibly need to happen? Or why does it actually help the deer population? Yes, too many deer, more starvation for deer, more disease for the deer, etc. There's reasons. So there aren't as many natural predators anymore around to actually have the population be in balance. So anyway, I went off the tangent, but it's trying to make you think about why there's a ceiling. So can you have an unlimited amount of fish in a lake? No, you can't. They won't be able to breathe if there's too many fish in the lake. They will run out of oxygen. There won't be enough to sustain them all, and they'll poop too much, and they'll be disgusting. I mean, come on, guys. There's only so many fish. There's only so many fish you can put in your fish tank. There's a limit. So that's called your saturation point. A logistic function models the S-curve of growth of some set or generally random population. All right. They go like this. Okay. It's approximately exponential, and then as saturation begins, the growth slows. At some point, the growth stops. So, with what I just said, Try to tell me what you think the ceiling is, hint, hint, on this population. Just look at the equation. 18. There you go. That's the ceiling. It's on the top. They can't sustain more than that many fish in this lake. So this population of a certain species, I'm trying to make this connect so you'll remember what these numbers mean. So graph the function. We're going to use our graphing calculator. So we're going to pop this in there. Okay, let's see if I have to clear some. Oh, I keep hitting the wrong button. Oh, don't do that. Okay, I hit the stat button somehow. Oh, I already have it in here, don't I? Is that it? What a beautiful thing. Okay, so there's our graph. That's what we need to put in for the graph. That's just the equation that you're given. Try hitting zoom 0 to get it to fit. Okay, what do you think the asymptote is? Looks like there might be an asymptote to this graph. It's, what did I tell, what's the ceiling? Yeah, 1880, that's your asymptote. Now, guys, we need to know the initial value. We want the y-intercept. So let's go like this. Second trace. Oh, my pen just went wacko on me. Second trace. Okay, I want to put in a value because I can't see the y-intercept very well because they're so big, the graph's so big, so or stretched. If you hit 1 and put in 0 for x, it will give you your y-intercept, which is about 777 fish. Okay, the y value 770 when x is 0. So about 777 fish. That's your initial population of fish. So let's estimate, on our graph, I know I did not estimate that well. The horizontal asymptote, y is equal to 1800. I'm going to just, dash that into your graph. You were going to be required to have these. By the way, we could have done something else with our graph if the zoom 0 didn't work for you. Did anybody have that problem? Okay, so let me show you something because I did earlier today too once. Go to your window so you can see your graph better. Isn't there a suggested window right on our paper? Okay, 0 to, it says 250 or 300 I think is fine. Okay, leave the scale of 1, that doesn't matter. Put in for y's 0, and then it says up to 2500. I don't know why we had to go that high. And now hit graph. Okay. Can you see it now better? Yeah. All right. Sorry, I forgot to do that. Now the question, we have one more question. It says, what does this 1880 represent? And we said it was the saturation level. There can be no more than this number of fish. You will need to be able to explain that what that means. And when will the population reach 1,875 fishes? So you're going to put in y2, 1875, graph, and calculate the intersection. Okay, I went 3 times about 170. And was that in years? Yes, okay, about 170 years. I hope you enjoyed the applications of logarithms.